All right, we have 2 sections left this semester. In section 6.7, we are going to be talking about Stokes Theorem. And Stokes Theorem is really just a higher dimensional version of part of Green's theorem. So on the screen right now, I have just jotted down the circulation form of Green's theorem. So we learned a while back that we can take basically a line integral over a vector field along a closed path, and we can rewrite that as a double integral over the area of the region enclosed by that curve, but we're going to be integrating this nx minus my, which actually is the curl of a two-dimensional vector field. All right, so here is Stokes theorem, and this is really just a three-dimensional version of that circulation form of Green's theorem. So now we're in 3D. We're saying the same line integral over a closed path with a positive or counterclockwise orientation over a three-dimensional vector field can be rewritten as the following integral. We can rewrite that as integrating the curl of that vector field over the surface that has a boundary of C. All right, there's a lot going on with this theorem. I think it's kind of hard to visualize, so let's just do an example and I'll see if I can explain it through my example. So right here on the screen though, this is Stokes theorem. This is what we're going to be using in this section. So basically the first thing I want to do is, for a specific example, I want to compute my line integral, which was the left side of Stokes theorem, and then I'm actually going to compute the integral of the curl of the vector field along the surface described, and that was the right side of Stokes theorem. So we're going to solve a problem two different ways, by creating a line integral and by integrating over the curl over a surface. And hopefully we get the same answer. We should get the same answer because that's what this theorem is telling us. So this is the problem I want to focus on to kind of explain Stokes theorem. So the surface we're going to consider is the plane x plus y plus z equals 1. And we're just going to consider the piece of it that lies in the first octant. And our vector field is negative y squared, comma negative 2xy, comma yz. All right, so here's a picture of what we are working with. So the surface we're working with is just the portion of this plane that lies in the first octant. And so what Stokes theorem is telling us is that if we integrate this vector field along the path of this boundary, so I've labeled the boundary C1, C2, C3, and I have it in a positive or counterclockwise orientation. So Stokes theorem is telling me if I integrate my vector field along this boundary, I will get the same answer if I integrate the curl of my vector field across the surface that I have shaded in blue. So really, this is a three-dimensional version of Green's theorem. In Green's theorem, we were just considering things on an xy plane, but now, all of a sudden, you can kind of think of it as I've tilted this. We're allowing things to happen in 3 dimensions. All right, so I am going to compute these integrals, this problem. I'm going to solve this problem in 2 different ways. I'm going to compute my line integral, and then I'm going to compute the following integral, curl of my vector field over the surface in blue. All right, so we're going to start with our line integral. Unfortunately, we're going to have to set it up as 3 separate line integrals. We have to do each part of this path separately. So I'll say C1 is the piece on the bottom. If you look at your plane x plus y plus z equals 1, plug in 0 for z, you've got the line x plus y equals 1. So that's the line we're thinking about. And so I notice the x values, I didn't label it, but my intercepts are all 1. So the x values start at 1 and they go to 0. And the y values start at 0 and they go to 1. And so I thought it would be easiest if I just let y equals t, because the y values are getting bigger. The y values are going from 0 to 1. So I chose to make y equal to t. And then if y is t, x would be 1 minus t. And then my t values can go from 0 to 1. This line C1 is in the xy plane, so the z values are always 0. So there's parametric form of that first part of my path. And then C2 lies in the yz plane, so the x values are always 0. This line has the equation y plus z equals 1. Put in x equals 0, y plus z equals 1. Let's see, the y values are decreasing. They're going from 1 to 0, but the z values are increasing. They're going from 0 to 1. So I decided to make z equal to t. If z is t, y would be 1 minus t. And then the x's are always 0. I can make my t values go from 0 to 1 because that's what's happening here. The z's are going from 0 to 1. Okay, one more path in the xz plane here. I'm calling this C3. Now my x values are increasing. They're starting at 0. They're going to 1. My z values are decreasing, starting at 1, going down to 0. So I decided to make x equal to t. So if x is t, then z would be 1 minus t. Just using that equation, x plus z equals 1. Let's see, the y's are always 0. And again, we can make our t values go from 0 to 1. So I have my 3 different paths written in parametric form. And then to compute these line integrals, I am going to take my vector field, which is f, dotted with r prime, and that's what I'm going to be integrating. Okay, so we're going to take f dotted with r prime. And so let's just do one at a time. Let's start with C1. So let's start with that path C1. So in vector form, C1 has x values of 1 minus t, y values of t, z values of 0. So that's my r. R prime, the derivative of this would be negative 1, 1, 0. Okay, so there's my r prime. All right, and so my vector field, the vector field given was this negative y squared, negative 2xy, yz. And so I'm going to take that vector field and I'm just going to rewrite it in terms of t. And so I use the parametric equations. Again, I'm just dealing with C1 right now. So I use my parametric equations, x equal 1 minus t, y equals t, z equals 0, and I just went ahead and plugged that in to my vector field. So let's see, the negative y squared, that's why that became negative t squared, and the negative 2xy, I put 1 minus t in for x, t in for y, and then this yz just becomes 0 because z is 0. So I've got a negative t squared, negative 2t plus 2t squared, comma 0. So I took my vector field, I rewrote it in terms of t, and then I'm going to take the dot product of f and r prime. So my r prime is in this circled box, negative 1, 1, 0. So take the dot product of f with r prime. So negative 1 times negative t squared, that's where the t squared came from. And then 1 times negative 2t plus 2t squared. Combine like terms, I got 3t squared minus 2t. So that's my f dot r prime. And then finally, I am going to integrate the 3t squared minus 2t, and I'll be integrating that from 0 to 1. So antiderivative was t to the third minus t squared. I plugged in the 1, I plugged in the 0, and this just ended up being equal to 0. Okay, so lots of work, answer of 0. We are 1/3 of the way done. So what I've done right now is I've just figured out that when I integrate this vector field along that path C1, I get 0. And so I'm just going to jot that down over to the side so I don't forget that. So integrate along C1, we get 0. And now I'm going to move to C2, and I'm going to try to do the exact same thing. So I'm going to use now the parametric equations for C2 to compute my R prime, and I'll rewrite my vector field in terms of t. But now I'm using the parametric equations from C2. So now I'm replacing the x's with 0, the y's with 1 minus t, the z with t. And so I ended up getting, it's the same vector field, but different parametric equations. So I got negative 1 minus t squared. Oh, x is 0, so the middle component is 0. And then the last component is a 1 minus t comma, or times t. Yeah, y times z. So 1 minus t times t. I distributed, so I did actually FOIL out the 1 minus t squared, and then I distributed the negative. So that's how I got this minus 1 plus 2t minus t squared. Middle component is 0, and then I distributed the t in that last component. All right, let's see what next. So we got our vector field. Now we got to find our r prime. So we can do f dot r prime. And so the r is given by my parametric equations. So the derivative of each, derivative of 0 is 0. The derivative of the y is negative 1. Derivative of my z expression is 1. So I'm going to take f dotted with r prime. So 0 times the first component is 0. Negative 1 times 0 is 0. Okay, so we're just left with 1 times t minus t squared. That's just t minus t squared. So the quantity I'm going to integrate is t minus t squared, and I'll integrate that from 0 to 1. So I have my work on the screen. Antiderivative was t squared over 2 minus t to the third over 3. Plugged in 1, plugged in 0, did some arithmetic, and I ended up getting an answer of 1/6. So I have just shown that when we integrate along this path that I have labeled C2, if we integrate our vector field along that path, we end up getting 1/6. All right, one more path to do. Third path. And so I just jotted down here just so I don't forget. Let's see, we got 0 for the path 1, 1/6 for path 2. Now we're going to do path 3. So same process, different parametric equations. So I'm going to rewrite my vector field using my parametric equations for C3. Oh, this is kind of convenient. Look what happened here. Because y was 0, the first component of our vector field is 0. Well, the second component is 0, and the third one is 0. Well, that's kind of nice. So my vector field just turns into 0 when y is 0. And so it doesn't even matter what r prime is. If we take the dot product of this 0 vector with any vector, we get 0. And then if we integrate 0, we're going to get 0. So at least the third one was a little bit faster there. So then finally, for my final answer, I'm going to add up all of these answers. So C1 we got 0, C2 we got 1/6, C3 we got 0. Add them all up. Final answer is 1/6. Okay, so what we've done right here is we have integrated a vector field over a closed path in 3 dimensions. path is oriented in a positive direction, which it means counterclockwise. All right, so what Stokes' theorem is telling us is that we should get the exact same answer if we integrate the curl of this vector field over the surface that I have shaded in blue. And we want to orient that surface in a positive direction, so we want to make sure that our normal vector is pointing upward, has a positive z component. All right, so same picture, but now what we're going to do, we're doing part B of this problem. We're going to compute the curl of our vector field, and then we're going to integrate that over our surface. So I'm going to use this determinant notation to help me compute the curl. You can think of the curl as your del cross f. So I just put in my partial derivatives, ddx, ddy, ddz, and then I just copied down the components of my vector field, the negative y squared, negative 2xy, yz. And then let's see, I'll go through and find, let me get my pen, go through and find each of those. So for my I component, I have to take the derivative of yz with respect to y. I got z. And then I'll subtract, here it is, the derivative of negative 2xy with respect to z. Well, that's just 0. So there's my I component. Let's see, j component. So I'm going to take the derivative of yz with respect to x. Well, that's 0. Negative y squared with respect to z. That's also 0. And then finally for the k component, let's see, derivative of negative 2xy with respect to x. That's the negative 2y. And then minus derivative of negative y squared with respect to y. So minus a negative 2y, that's going to become a plus 2y. So this actually simplifies down to z, 0, 0. So the only component that is not 0 is the first one, and it's z. All right, so that vector is the curl of my vector field. And so now what I'm going to do is I'm going to be integrating my curl over this surface. And to do that, we are going to take the dot product of our curl, which we just computed, with, technically we're taking its dot product with our normal vector. We want to make sure our normal vector is pointing up. And that normal vector, let's see, we called negative gx, negative gy, comma 1. So we want to make sure that that z component is just 1. And this is the normal vector of our surface. Our surface right here is the plane x plus y plus z equals 1. So I went ahead and solved that for z. So here we go. Z equals 1 minus x minus y. Derivative with respect to x is negative 1. Derivative with respect to y is negative 1. So then the vector that I'm dotting it with, my normal vector, is going to be negative gx. So negative negative 1 is 1. Negative gy is also 1, and then comma 1. And so this is essentially, it's a vector that points, can't really draw it here, but there we go. It's pointing out, it's perpendicular to this surface, or orthogonal to that surface. So it is technically our normal vector. All right, so to compute our surface integral, we are going to take the dot product of our curl, which we computed, with our normal vector, and we're going to integrate that over the projection of the surface in the xy plane. Okay, so we'll do our dot product first. The dot product is just z, because you get z times 1 plus a bunch of zeros. And the area that we're going to integrate that over, I've tried to shade in. It's our projection of the surface in the xy plane. So that little triangular region. So 2 things I'm going to do here. Again, we're trying to find this integral. We're integrating z over the area that I have drawn on the top right of the screen. So 2 things I have to do here to set up this integral and solve it. I want to use the equation of my surface to rewrite the function I'm integrating in terms of x and y. So I am going to substitute or plug in the 1 minus x minus y in for z. So I just replaced the z with 1 minus x minus y from that surface. All right, so that's the first thing we're going to do. And then we're going to set up our integral to integrate over the area of this region. So if I want to do the y's first, the y's go from 0 to 1 minus x, and the x's go from 0 to 1. All right, so this integral, this is our surface integral, and hopefully we get an answer of 1/6, because that's what we got when we did our line integral. All right, so I'm going to start by integrating with respect to y. I got y minus xy minus y squared over 2. Plug in my bounds of integration, so I'm going to plug in the 1 minus x, plug in the 0, I get 0 for that. So really just have to plug in the 1 minus x. And then I'm going to do some simplifying. You could just distribute, combine like terms. I did a little bit of algebra trickery here. So let me show you what I did. I noticed that these first 2 terms here, if I factor a 1 minus x out, I'm left with a 1 minus x. So I noticed that from these first 2 terms. So these first 2 terms can be factored as 1 minus x, 1 minus x, and I can write that as 1 minus x squared. So this problem is now 1 minus x squared, then minus 1/2 x squared, and then I can combine those like terms. 1 minus 1/2 is 1/2, and I can rewrite this as 1/2 1 minus x squared. All right, so I got 1/2 1 minus x squared. Again, let me go back. If this didn't make sense to you and you just would prefer to just distribute, FOIL everything out, combine like terms, that would be a great strategy as well. All right, so now we are going to integrate our 1/2 1 minus x squared with respect to x. Rather than expanding it, I used a u substitution, and I ended up getting a 1/6 1 minus x squared divided by -1. I'm going to plug in my bounds of integration. So plug in the 1, plug in the 0, subtract them, and fortunately I did get 1/6, which was the same answer I got before. And that should happen. That's what Stokes' theorem is telling us. It's telling us we should get the exact same answer. Okay, so if we have a closed path in 3 dimensions, we can rewrite that line integral over that closed path, that line integral of the vector field, as a surface integral by integrating the curl of that vector field. In some cases, I think honestly the line integral is easier, and in some cases the surface integral is easier. Kind of just depends on what you're dealing with. So let's do one more example. Let's use Stokes' theorem to evaluate this line integral f dot dr for the vector field given, and they're telling us to use the surface 9 minus x squared minus y squared. Z is bigger than or equal to 0. So the surface that they want us to use is a paraboloid that opens down and basically stops on the xy plane. So the z values are always positive, so it stops at the xy plane. So the boundary of this particular surface, the ends of this surface would actually be on that xy plane. And so I've tried to draw in blue there. That is actually the path that technically we are computing this line integral for. All right, but they want us to use Stokes' theorem and actually compute this as a surface integral. So what we're doing, just to kind of illustrate again Stokes' theorem, is if we were to integrate our vector field over this path that I have drawn in blue, we will get the same answer as integrating the curl of our vector field over the surface that I have shown in green. All right, I'm going to set up my surface integral using Stokes' theorem. So the first thing I have to do is find the curl of my vector field. So I set up my determinant notation for del cross F. So I'm going to go ahead and find derivative of 4xy with respect to y. That's 4x. Derivative of y with respect to z is just 0. And then negative derivative of 4xy with respect to x is 4y. Derivative of xz with respect to z is x. And then last component, derivative of y with respect to x is 0. Derivative of xz with respect to y is 0. Okay, so the curl then is this vector 4x negative 4y plus x, comma 0. All right, so we are going to be integrating our curl over the surface that was given. And the surface they gave me is z equals 9 minus x squared minus y squared. So you can think of that as my g. So the surface given, z equals 9 minus x squared minus y squared. I'm going to find my normal vector by taking, let me write it down again for you. I'm going to find negative gx, negative gy, comma 1. Okay, so gx is negative 2x, gy is negative 2y. I change the sign of those. I get 2x, 2y, and then comma 1. So that is my upward pointing normal vector. So then we're going to take the dot product of our curl with our normal vector, multiplying the corresponding components, adding them together. I ended up getting 8x squared minus 8y squared plus 2xy. All right, so we are going to integrate, again, curl dotted with our normal vector, and we're going to integrate that over the projection of our surface in the xy plane. So I've shaded it in blue, the projection of that surface in the xy plane. So we're going to be integrating this over a circle. It would be a circle of radius 3. You can see that if you plug in 0 for z into our surface. So that's the circle that we're going to be integrating over. All right, so we're going to be integrating this over the circle x squared plus y squared equals 9. Because we have a circle, I think working in polar coordinates is a good idea. So I'm going to go ahead and convert everything into polar coordinates. And I have already done that. Let's see, in blue on the screen, I replaced the x with r cosine theta, and I replaced the y with r sine theta. Same thing in this last term. X is r cosine theta, y is r sine theta. And then the dA became an r dr d theta. My bounds of integration for this circle, the radiuses go from 0 to 3, and we're going all the way around, so the thetas go from 0 to 2 pi. I decided to, just to save myself a tiny bit of writing, I factored out the r's because I'm going to integrate with respect to r first. So I noticed all of these terms have an r squared in them. If I distribute or multiply by that extra r, now all of my terms have an r to the third in them. So I just factored that r to the third out front, because now when I integrate with respect to r, the r to the third becomes an r to the fourth over 4, and then I just copy down the rest of these trig functions. So we were left with an 8 cosine squared minus 8 sine squared plus 2 sine theta cosine theta. I'm going to plug in my bounds of integration in for r. So I plug in the 3, plug in the 0, subtract them. I got 81/4 times all of those trig functions. So finally, to finish this problem, I am going to integrate with respect to theta. Before I do that, I probably need to do some simplifying. A couple of ways you can do this. You might recognize some double angle identities. You could use those to simplify them. I'm going to go ahead and use my power reduction identities. That's typically how I deal with cosine squareds and sine squareds. So I am going to replace the cosine squared with 1 plus cosine 2 theta over 2. I got 4 plus 4 cosine 2 theta. And then I'm going to go ahead and replace my sine squared with 1 minus cosine 2 theta over 2. So I ended up getting -4 plus 4 cosine 2 theta. I did some distributing in my head there. So technically it was, let's see, the cosine squared became 4 plus 4 cosine 2 theta. And then we have a minus 4 minus cosine 2 theta. There we go. A little messy, but that's why I ended up getting a plus with the 4 cosine 2 theta. Okay, so algebra, trig, simplifying this down. Let's see, so now this 4 cosine squared, no, sorry, 8 cosine squared minus 8 sine squared. We can replace that with 4 cosine 2 theta plus 4 cosine 2 theta, which is 8 cosine 2 theta. The other way of doing this is maybe, I don't know if any of you recognize this from trigonometry, but cosine squared minus sine squared is actually cosine 2 theta. That's my double angle identity, so 8 cosine 2 theta. All right, and then I'm going to just leave that 2 sine theta cosine theta alone because I can integrate that as is. If you want, I think you could use a different double angle identity there. But I'm just going to leave it as it is. And now I'm ready to do my integration. So the 8 cosine 2 theta becomes 8 sine 2 theta over 2. And then for the second term, that 2 sine theta cosine theta, the u is sine theta, so the du would be cosine theta. We integrate that, we're going to get u squared over 2, or I guess 2u squared over 2. So 2 sine squared over 2, or just sine squared. And so finally, I'm ready to plug in my bounds of integration. I'm going to plug 2 pi in. I'm going to plug in 0 and subtract them. And let's see, I get a bunch of zeros there. Yeah, all of those signs turn into zeros. And my final answer here is 0. Now, Stokes' theorem says, had we integrated along the pathway, we would have gotten the exact same answer. So we should also get 0, so you could try that. If you integrate along that path, you'd have to come up with parametric equations for your path, and then you could integrate the vector field along the path. You should also get 0. Because these surface integrals are equivalent to that path integral, it actually turns out you could compute this integral using any surface that has the same boundary. So in this case, we had a paraboloid, but you could use a plane or a sphere or any type of surface at all with the same boundary should give you the exact same answer. And so that's one of kind of the interesting consequences of Stokes' theorem, is it turns out any surface with the same boundary, when you integrate the curl over those surfaces, you'll get the exact same answer. All right, so that was my last example. Please let me know if there's anything I can clear up in this video.